Now, this part, we're going to look at a new coordinate system. We will use cylindrical components. All right. This you can read lah. Huh? So we'll look at what is polar coordinates. I think you can relate this one to your static module or dynamic module, right? So let's see if you have particles that move in the curvilinear motion. I just mark as a red ball here. So the location of particles on a curvilinear curve, you can define by the origin to the location of the particles. I label as R. I label as R to represent from the origin of your observing of the observer, or you standing here, you look at the particles. That is a distance that we call R in polar coordinates. Huh? So we are now talking about a new coordinate system in terms of polar coordinates. So the distance from the origin to the object we call R. In this case, in polar coordinate, we start to use the radial coordinate. We will label our axis, the new axis, not new lah, but a new name for polar coordinates. The axis that follow your R direction, we will label as R. Right? And there's a reference point. There's a horizontal reference point. You can take this one as your imaginary reference point. Normally it's a flat horizon. Right? Flat horizon. And then you can measure the angle of the theta. The angle between reference line and the location or position line R is defined with the direction. The positive direction will be anti-clockwise. Take note, huh? The reference, the direction of the angle measured from reference line we will treat positive in the anti-clockwise direction. Huh? And we apply this one in all the scenario for polar coordinates. Okay, in polar coordinate scenario. Okay, so far we have the origin, we have the R to the particles, which is a position in the unit of R. We measure the location by using a reference line and the angle. And if you have a positive angle, it means that you are referring in the anti-clockwise direction from a reference line. Again, I highlight with the red color over there, just to mention that it's important. And this angle we call transverse coordinate. So we have two types of coordinate here. Under polar coordinates, under coordinate, you refer your item or your object using two axes or two coordinate. One is R, named as a radial coordinate. Another one is angle. In this one, we name as transverse coordinate theta. Okay, so it's a little bit different from the tangent and normal direction just now. Okay, if you define something in the tangent normal, then you'll see T and N. However, when you define your problem using polar coordinate with the R and theta, then you need to be careful on the direction, right? Especially the angle anti-clockwise is positive. And it refers from the reference line that you draw to solve the overall system. Huh? This is the domain or the reference, the principal reference line to solve the overall system. All systems refer to this reference line. Okay. So first, identify what is R, what is theta. Okay, theta is a location. Huh? It's a coordinate. Sorry, it's not location, but it's a coordinate. It's a transverse coordinate. R is a radial coordinate. So we further upgrade a little bit our diagram over here, our free body diagram. So again, you know that vector have magnitude and direction. Let's look at direction first. So again, you can draw two axes on the object. Since we are talking about polar coordinates, you have two axes. One is r, one is theta. Again, theta is a transverse coordinate. Okay, direction of the changes of your transverse direction, which is from the reference line. If you anti-clockwise, it going pointing up, right? So you follow the direction. Huh? This one anti-clockwise. So anti-clockwise, it means it makes this line to go up, right? So the direction of your theta is going up. And again, the angle between your theta and your r is 90 degree. Okay, so when you solve problem using polar coordinates, remember you are using r and theta and not t and n anymore. It's not tangent and normal. It's no longer use tangent and normal anymore, but we use r and theta. And see if you're able to relate how to draw the r axis. It's always follow the direction of your position, r. Okay. All right. Next, we will input the unit vector for r, unit vector for theta or transverse coordinates. Again, u sub r means in the r direction. U sub theta, it means in transverse direction. U theta, ur. And this is a direction. This is a direction and not confused with the u for velocity. This is a vector direction. Vector direction. Right? Okay. Next, we look at the motion. Once you are clear with this schematic diagram for polar coordinates, you know about the unit, you know about the position, you know about the transverse coordinate theta, you know about the axis of radial and transverse, you know about the direction of ur, direction of u theta. Then we look at the changes of motion now. Okay, read this statement, see if you understand. ur is in the direction of increasing r when theta is held fixed. It means this one, ur will always follow the r axis in this direction, while the angle doesn't change. Mean this one fixed. When you fix this one, your ur will travel along r. Okay, it will travel along r axis in this direction. Okay, because we try to relate your ur and theta later on. So now the direction of ur, it can be increasing along the r with one condition. This one must be fixed. This angle must be fixed. If you want to increase direction of your, or you want to fix the direction of your ur along the r axis here. Second statement, read if you're able to understand. Now we focus on this component, the transverse coordinate direction. U theta is a direction of increasing theta when r is held fixed. This direction can increasing in the theta axis with one condition. Your r cannot be changed. Your r must be fixed all the way of the direction of the u theta. Okay, so when you talk about ur increasing, when you talk about ur direction increasing in r direction, there's no change of theta here or transverse coordinate here. When you talk about the increasing of u theta here along the theta direction, when it's increasing in the theta direction, there's one condition. Your r must be fixed. There's no changes of r. Huh? So this is the relationship between ur theta and u theta and r. This is a fundamental concept before we go into equation later on. Okay. Okay. All right. Yeah, this is just further information. We already explained that theta and r always 90 degrees. We already done the general positive, negative, how they relate to each other. Okay. Now we look at velocity, position first. We derive an equation to find the position in a polar coordinates format. We can use vector of r to represent position. This orange color with an arrowhead is a vector. Position, in this case, position is a vector in a polar coordinate system. R is a vector. The characteristic of vector, you have two components inside vector, magnitude and direction. So when you write vector position for polar coordinates, you write magnitude and direction. R in orange color, which is a vector, position vector R equal to the magnitude of your R here. So from here to here is the blue color R. You can measure the vector length. The direction is following the yellow color UR. Okay, so direct magnitude, direction. This is how you define your R. Huh? As long as you hold on the concept of vector, you are okay. Huh? So don't run outside the understanding of vector. See the position as a vector, then everything will make sense. Huh? Of course, I use a dot there just to highlight. There's two different components. In the textbook, most textbook, they don't have dot here. They just give you R, UR. Right? Next, we look at our velocity. How do you plot velocity on the polar coordinates? So we will focus on R. We'll use R to find our velocity. So you know that velocity is a displacement over time, right? It's a displacement over time or position over time. So you have a position equation over here or vector equation here. You find velocity, you differentiate this one over time, or you take the whole equation divided by time, you get velocity. So V in green color equal to R dot. Okay, since the previous, a few more slides, I think the previous lecture, we already agree that every time you see something on top of the alphabet, there's a dot there, means we differentiate over time. Okay, M dot means menstrual rate, something dot above means you divide by time, or that you differentiate over time, the rate of something, something change over time. So V equal to R dot, you need to differentiate these two entity here. Again, go back to calculus. When you differentiate two equation, or you differentiate y equal to uv, how do you do it? How you differentiate y equal to uv? All right, there's a product equation there. So use that equation to solve this one. Meaning dr over dt, r here is a vector. Vector, you have magnitude and direction. So this is two equation here. You have u and v. I mean y equal to u and v, general equation in your calculus. All right, so you use product rules. You hold the first one, you differentiate this one, plus you hold this one, differentiate the another one. Okay, this called product rules. Okay, we use product rules. You'll get something like this. Okay, so if you're confused or you forget what is product rules, go back and Google what is product rules. You've done this one before in your junior years. In your junior years, you've done this before when you do differentiation. Y equal to UV, you use the product rules. This is how you do it. First, you can flip the sequence. No problem. You can flip the sequence. I will always hold the first one. I differentiate this one. I get this one. R du dt. Then plus, I hold this one. I differentiate R. So I get the R dt multiplied by du. You can flip the sequence, no problem, as long as it meet the product rules calculation. Okay. Next, because later we will look at a lots of equations, so we will try to simplify our symbol. So your dr dt we change to r with a dot above it to represent we divide over time, or we differentiate over time for this one, right? We change the dr over dt with r dot. Same with this one, ur dt. So we use ur with a dot above. So we have a new equation. If you want to find velocity, you use this equation, or you can use this equation, right? Same, right? Anything that you are not sure, you can ask me. I think clear. So far, we just deal with a simple equation, and maybe something confused here is product rules. Well, what is product rules? Go and look at your calculus textbook. What is product rules in the differentiation? Okay. We'll continue, because once you have a velocity, you know that we're going to find acceleration, right? So to find acceleration, what do? You differentiate over time one more time using the velocity, or a equal to dv over dt. You repeat the same process for the velocity. You use the product rules again. You get a very lengthy equation, right? But try to understand the process first. Now we try to put our u dot here in terms of something that you can relate to this diagram. Okay, because if you look at this, it's very difficult to process. We'll try to rewrite this one into something that related to u theta here. We want to relate this term either in ur or u theta. We want to change this term either in u theta or ur. Let's see how we do it. So now we focus on this term first. Later we will substitute back inside this equation. So now we focus on what is u dot r in terms of either this one or this one. So again, tell yourself ur is a vector. Vector have magnitude and direction. Okay, and ur only change in the direction with respect of time. What does it mean, right? So we will use these two statements to reproduce a new equation. First understanding is that ur, this one, only changes with time, and the magnitude of this one, magnitude of this direction, ur is the direction, right? It's a vector direction. Ur always have a magnitude of 1 unit. We always use 1 unit to calculate for our magnitude for direction. It's 1, always 1. So combine these two understanding, we write in the mathematic form. when there is a change of time, a little small changes of dr, meaning if you add a little bit here, will not cause a change in the direction of ur, because what the ur do is it will always follow the r direction. No matter it go, this one fixed, right? Just now we have an understanding of this component. ur, the definition of ur was staying at the r direction when you lock this direction, when you lock this transition coordinate theta here. So in mathematics, so another one is that a change of d theta will cause ur become u prime r. All right. So before this come into place, just now we mentioned about the definition of ur. ur will continue to travel in r when we don't change the theta. What happened if we change the theta here? What happened if we change the theta here? This one is going to change to a new direction. We give the new direction a new notation. We write u prime r. Okay. So I export this section. I export this section to a new space there. So this is original direction of your ur. But what happens if you change your transverse coordinate here? What happens if you increase or decrease? What happens? Right, let's say we increase the theta. There's a change of theta over here, positive, anti-clockwise. Right. So this is a theta axis, same, I just copy. If there's a change of delta theta here, transverse, your vector going to change to a new direction. It becomes u prime r with delta theta. This is two vector, right? So if you're given two vector, are you able to complete the triangular vector diagram? You're given two vector that is starting from origin. Are you able to complete the vector diagram if you're given two arrow in this case? Right? You're connecting the arrow head to arrow head. You will get delta ur. Again, this is the change of direction. ur is the direction, right? So delta ur is a change of direction from this arrowhead to that arrowhead. Okay, makes sense to you? Mathematically makes sense to you? Now we will use the vector diagram to derive the vector equation. Once you have the delta ur, are you able to derive the vector equation using this triangular? ur is your resultant, right? Resultant always from the end point to the, starting point to the end point. And from here, you have a combination of two vector ur and vector delta ur. You combine this vector and this vector, you get the resultant, right? This is how you draw the vector diagram. So you can write this equation using the understanding of the triangular vector diagram. So from here, you get resultant equal to all the vector combined. So here you write u prime r with this the slanted one. Your resultant or your hypotenuse of your triangular, or the arrow that's showing beginning to the end point of the vector, equal ur plus delta ur. You have the first equation that relate to the change of angle over here, change of transition coordinate over here. Okay. And now we talk about time. When there is a time change in ur, then we can write then okay, so this statement explain what is this. What is this? This is the changes in UR in the small time. So let's do a little bit more about mathematics. We assume that this angle or this change of angle, delta angle or delta angle there is very, very small. Then you can use the radial or radius definition in the circular, small section of circular. You still remember in mathematics when you have a pie shape or there's a small section of triangular, you can use the S equal to R theta. You still remember in mathematics? If not, you have to flip your mathematics textbook. Under radial calculation for small changes of circumference in the circle, right? It's all under circumference chapter about circle, right? Linked with the radian parameter. So if we have a small delta, we can write our vector, change of vector, will have our magnitude delta UR will be similar to 1 times the change of angle. So you know that if this is a circular and you can find the distance of the circumference by using S, the circumference S equal to R theta, you use the same approach. UR, okay, UR equal to 1 because you know that the magnitude of your the magnitude that you calculate for your delta UR will be 1. So you have this calculation. And the direction of your UR. Okay, the direction of your magnitude of your delta UR, the change of your velocity direction is in what direction? Is in transverse coordinate direction or theta direction. This one is going along parallel to the theta axis, right? So this statement will continue to derive equation. You can write delta R is a vector. Vector have a magnitude and direction. So delta R equal to, this is the magnitude that you calculate from here. Delta R equal to U theta, which is the direction. Right, from this vector diagram, you know that it is along the theta direction. So you can write delta UR equal to delta theta U theta. Make sense to you? Second equation. Next. Yeah. Go ahead. Any question?
No, sir. Makes sense, sir.
Next. Because this is a very, very small changes, mathematics, we will complete the equation or we will use limitation to change the delta, small changes to something that we can measure. We can change the delta triangular to D if you use the limitation, right? So this is what you learn in mathematics. Small changes, it become, if you have impose the limitation, you can change the formula delta to D. So what is the definition of U dot R? It's a change of your UR over time. Okay, what is your UR definition? Mathematically, delta UR equal to delta theta U theta. You substitute this one over here. You know that U theta is a direction, right? You know that U theta is a direction. So basically, it doesn't change. It doesn't make sense you monitor the direction. but you monitor the change of transverse delta over time, then it make more sense. So you can factor or you can pull the u theta outside. Okay. Then you arrive at the definition of u dot r equal theta dot. There's a theta dot above the theta, there's a dot there. Means you take the theta divided by time. Theta dot, blue color, on the top there's a dot there, u theta. Now you have a definition of the rate of change in the r direction. You relate with the angular changes of theta dot in the u theta direction. Okay. Recall just now the velocity equation. V equal to r dot ur plus r u dot r. You have the u dot r equation. Pull that equation, substitute over here. Okay. And then you put your ur one side, u theta one side. You have the magnitude, right? This is a magnitude direction. Magnitude direction. Once you have the magnitude direction in r, one of the direction in theta direction, you can know that you can always find the magnitudes. We're using the square root of this one square plus this one square, and then you square root, you get the magnitude of the v, by what you did for acceleration. So to simplify, we will use r dot, we will use a new notation, Vr to represent the r naught, V theta, V sub theta to represent r theta dot. Okay, so this is just a quick way when you want to extract this information into the calculation later on. But I personally prefer, I will always pull these two equations together. I'll pull these two equations together just to remind myself, you can calculate ur with this equation. You can calculate this u theta with this equation. Okay, I will always write these two equations together. Right? And remind myself, once I have the Vr, V theta, I can find the resultant magnitude between these two. And I can even draw or sketch this magnitude on the object using on the axis. So this one, Vr in the r direction. I have some number here. I can use my ruler to scale the length of the arrow. Same with this one. Okay, V theta also same. This is a magnitude. So I can use my ruler to measure how long is my arrow. And then to find the magnitude, I use the square root of this square plus this square. Okay, we have derived this equation. And what I explained just now is to find ur v u theta. So I just changed the diagram just now, right? I just changed the earlier diagram that you draw, this one. Same particles, same curvature, same reference point. I only use the axis to add on information. So I will transfer what I calculate Vr on this axis. I use green arrow to represent the magnitude of my velocity in r direction, and another arrow to represent the v theta in theta direction. This is a magnitude, magnitude of your velocity. Magnitude of your velocity. One is in r direction, one is in theta direction. And again, velocity is a vector. You have two vectors combined together. Use a rectangular or triangular if you want. But in this case, because it's a square, is a 90 degree to each other, I will just use a square to help me. So I draw a square flame, and if two vector is perpendicular to each other, I will use square, and I will just draw the middle point, and I get the resultant vector. Because I can always transfer, I can always transfer my UV, U theta to this side. It becomes a triangular vector diagram. Okay, so that's why I can draw a square, and then I can straight away draw from starting point to the another corner of my square diagram, because I can always move my vector from this location to this location with the same length. Okay, so this is how you find the magnitude of velocity: square plus square, square root. Right? Direction of velocity always tangent to the path. Direction of your v, your absolute v, your resultant v always tangent to the curve. Always tangent to the curve. And this definition doesn't change since the beginning of this chapter. Okay, since we do the linear motion and all this, not linear, called linear motion in the normal and tangent cases. This one also same in the polar coordinates. It always tangent to the curve, tangent to the curve. Okay, the velocity. Let's go to acceleration. Basically, it's the same. Basically, you use back, if you understand the acceleration just now, you understand the velocity derivation step just now. Now you do the same. You repeat the same procedure for the derivative of time over time, right? You take the v divided by time. You have the v equation, right? Recall just now. This is your v equation. But you don't need to memorize this one. Just try to understand the mathematics principle behind. What do we take to find acceleration? What do we take to find velocity, right? So in this case, acceleration is a velocity divided by time. So v dot. So just recall back, recall back. So what does it do? Again, this is two equation, right? Two equation. So basically, what is v dot? You take the v divided by time, or differentiate over time. So this whole equation integrate over time. So the method procedure, again, refer back to your mathematics calculus differentiation chapter, how to do this differentiation. All right. Then you'll get this very lengthy equation. Okay, so I'm not going deep into this equation, how to get this one, because this step to this step is under calculus differentiation chapter. But you arrive at this equation, which in this equation I highlight the direction and so also magnitude. I miss out this one. This one should be yeah, correct. This one is the R, correct. Okay, R. R. This one is the R, means is the vector R. Vector R. So you arrive at this one, or inside there, if you see double dot, something like that. Double dot means second order derivative, means you differentiate one time, you differentiate one more time. Okay. Now, for example, this one, this is an angle change, right? Angle change means is angle, the rate of change of your angle. What happens if you differentiate one more time? It becomes acceleration of your angle, angular acceleration. This one become angular acceleration. This one is angular velocity. This is angular velocity because this is the change of angle over time. So it's angular velocity. This double dot is acceleration because it's like It's like you differentiate velocity one more time, you get acceleration. Okay, so again, this is might be your homework if you want to go into detail how to get from here to here, but I'm not going there, right? So important you understand how you get this one, right? You differentiate over time using V equation. Then from here, there's a step to find what is this one. What is U dot theta? Okay, there's a step there. Okay, so again, this is U theta dot. So we need to recall the understanding of the polar coordinate. First, we need to find the change in the direction of U theta. Okay, so this is the UR direction in the R direction. This is the U theta in theta direction. This is what we know. What happens if you change this one? Just now we changed R, right? But now we want to find what happened if we change this one. When we change this magnitude, what changes? Okay, when you change U theta become a new direction. Okay, when you have a change of delta theta, your U theta become a new direction. We label as U prime or U comma theta. Again, in this case, the change of direction is anti-clockwise, positive. So this one stay. We look at the change of this one, because we want to see what is this U dot theta. So U dot theta is a change of this axis. So what happens if we change this axis and what are the equations involved? So we fix this one and then something happened to this direction with the delta angle. You become a new vector U prime theta. Okay, now you close, now you close you close this one. You don't want to see the UR anymore. Focus on this side. You haven't two vector there. Same, when you have two vector, you can complete the triangular of the vector, right? You can connect this point to get the delta U theta, right? Like what you did just now for the R, but now you did for the theta. So you connect this point to this point. Again, once you connect, you have a triangular vector diagram. You know which one is resultant, right? This one is from the beginning to the end. This one become resultant. Resultant equal to the products of this one plus this one. This one plus this one. So from this diagram, you can write a new vector equation. Okay, the rest is the same. You read. Okay. The next step is that I want to show you the equation of this one. Okay, so from this triangular vector, resultant equal to summation of all the vector from the beginning until the end. So you have two vector here equal to this one plus this one. Okay, we have one equation here. Basically the same principle. The time change in the U theta direction, we can write as delta U theta. Again, the vector have a magnitude, but the magnitude is 1. The magnitude of this vector here is 1. So delta U theta equal to 1. 1 times delta this one. Okay. However, you see this delta, this one, the delta U theta. Focus on this delta U theta vector. See what is different from the direction of your R. We define our R positive in this direction. But what happens if you already, after you completing the vector diagram, it pointing to this direction, which is opposite of your R. So when you write your vector later, this is the direction that is opposite to your R. Okay, so I write a statement here. This vector, it at negative UR direction, which is it opposite of this direction. You can write this one, delta U theta equal to magnitude and direction. Magnitude, we calculate. Direction, we convert into R direction, but it's the opposite. That's why there's a negative sign in this equation. Because this one, the direction is opposite of your UR. Okay, there's a negative delta, negative magnitude and direction. Okay, now again, we use the limitation to remove all the delta symbol in our calculation. So U dot theta, basically we take this one divided by time, because there's a dot there, there's a dot above. So basically we take this one divided by time, divided by time. You know that this is the direction. Direction over time have no meaning. Because this whole thing divided by time, so basically this is the one that you can divide by time. So that's why you get a negative theta dot UR. Okay, so from here, you do some limitation, you arrive at this one. Okay, I pull this equation to here and I erase all the equation on the board. You have two equations here. Recall this very lengthy equation. Substitute this one inside there because you want to remove all the theta, theta, theta means the U theta, U theta, U theta into R form. This is just add-on information. What I mean by R double dot? It means you double differentiation of second order derivative of your angle. It means you double, you differentiate and then you differentiate one more time. This is the angular acceleration, just add-on information. You substitution and then you do differentiation if needed because, for example, U dot R, U theta dot. Okay. Then you'll get something like this. A equal to R double dot minus R dot square magnitude. I purposely put a color with a bracket just to differentiate between magnitude and direction so that you know that this is a vector. So magnitude and direction plus the transverse direction U theta also have a magnitude. U theta double dot plus U R dot theta dot. Okay. In test, I won't expect you to write this one, but I expect you to write this one. Okay. This is standard, standard already. I don't expect you to derive equation, but I expect you to apply equation. Again, you can simplify this equation in this form. The blue color in front, in R direction, you can write as AR. The blue color in theta direction, you can write as A theta. Again, you have two directions, R and theta. You can plot inside your diagram using R and theta axis. And since you have two magnitude there, you can find the resultant magnitude of the acceleration using the same square plus square and then you square root. So I pull the equation side by side. Normally, when you solve a polar coordinate question, you need these two equations. I will just copy these two and put in my answer. Then I do calculation and then I plot. For this module, we expect you to know how to sketch, how to do a free body diagram. So when you derive for V or A, we expect you to draw the arrow inside the diagram. So here, I believe you know how to draw the AR, right? From the center of the object, draw R direction. You know how to draw A theta, right? So from the center object, draw to the direction of theta. You have two arrows like this. You're able to find resultant, right? Do the same like velocity just now. Draw a square from the starting point to the another corner. You get your resultant, or you can move this one to this one. You get a triangular. You solve for the resultant. Magnitude, same equation, same principle, but you take the front bracket square, take the second bracket square, and then square root. Same principle that you learn in your vector chapter in mathematics, but now you just substitute the equation inside to find. Okay, direction, you have angle, right? There's angle here, right? Direction. So there's a triangular. You have a right angle triangular here. You have your y, you have your x, you have your theta here. So you use tangent theta over here equal to the opposite divided by side. You can get the angle, right? But anyway, this is how you find lah. This is the thing that you can find, right? Okay, we solve for the 2D first. 3D, yeah, okay, we go for all these slides. So for 3D, basically, we will not go deep into derivation. It just tell you that when it comes to 3D cases, you have z-axis, where at that point of particles, you have your r direction, you have your theta direction, you have your z direction or your elevation direction from the origin. So from this diagram, it's quite direct. How to find the theta, how to find the r, how to find the z. Okay, so from the origin, you draw a straight line down. This is the elevation from the origin. Z represent elevation. How to calculate the r? You measure from the z direction, z axis, to the origin. That you get r. How you get the transverse angle theta? You measure from a reference direction, from a reference axis. You measure anti-clockwise also. Okay, anti-clockwise direction for your transverse theta. And this one is standard equation if you have this scenario, 3D scenario. How to find the r? You use this equation. Again, this is a vector. Vector have magnitude, magnitude, direction, direction. Okay, r magnitude, z magnitude, r direction, z direction. Same with the v. How to find v? You differentiate your r here. You get this equation. So for your velocity, you have r dot ur. Again, magnitude. This one is r dot means the change of your r. Ur is the direction. R theta dot in the theta direction. Z dot uz is a z direction, and so on. A equal to this one. Okay. A equal to this one plus this one plus this one. Okay, because this one is a three-dimensional cases, you have these three equations. Just a good news to share with you. For this module, I won't test you in three-dimensional. So this is just information for you that, oh, you've seen this one before, right? And if you go into deeper in other higher level of learning, then we will apply this three-dimensional question. So for this module, I won't ask you three-dimensional question. I'll ask you two-dimensional question. All right. Okay. I think we stop here. Next lecture, we look at tutorial question. Stop here.